Okay, our final speaker for today is Tamara Broderick, Associate Professor in MIT's Department of Electrical Engineering and Computer Science. Her recent research focuses on fast, easy to use, and reliable methods for quantifying uncertainty and robustness. Tamara's work has been recognized with numerous awards, such as the Presidential Early Career Award for Scientists and Engineers. And today she will outline key challenges that we must solve to automate science. Please welcome Tamara Broderick.
Awesome. Yeah, thanks so much. Thanks for an amazing set of talks today. It's great to be here. I'm hoping my talk will be pretty complementary to what we've heard so far. So far we've heard a lot of, I think, really exciting ideas for accelerating science. And I'm hoping to talk about some challenges in automating the full scientific pipeline going forward. We've already heard about plenty of, I think, super interesting challenges from a number of different speakers. And so I'm definitely not going to be exhaustive. Rather, I'd like to focus in on evaluation, and which I think is often underappreciated, and talk about how it's both interesting, important, and non-trivial. So I'm going to be talking about work with a bunch of super cool people today. I just want to highlight amazing work from my PhD students, my postdocs, and also our fantastic collaborators. Okay, to super high level today, I think we've been really thinking about how there have been really big changes to science in recent decades. So of course, I think in the theme of this conference, some of those changes have been from artificial intelligence. But I also want to point out there have been really big changes from computing, from engineering, from laboratory advances. In all of these cases, we have gotten new methods for hypothesis generation, for experimental design, for data collection that have fundamentally changed science in really exciting ways. I think the point of all of this, fundamentally, is to improve people's lives and generate new knowledge. And so, we're hoping, I think, at the end of all of these advances to get to the point where we say, we have some exciting new medical intervention that's going to save lives. We have some exciting new financial policy that's going to improve people's personal finance. Or we have some exciting new educational idea that's going to make education just strictly better for people. And so because these are such incredibly important areas where the results really, really matter, we need to make sure we're doing it right, that we truly are improving lives. I think we have to ask very carefully and make sure we're very sure that, in fact, we're sure it does work, that these methods really are working. And so to sort of get us in the frame of thinking about evaluation here, let me just look at a super high level typical setup for how we're doing science. First, we run a data analysis on some available data, and we conclude, did this intervention work? Was it actually helping people? Essentially, we're evaluating on this data. But of course, the whole point is not to apply that intervention to those people or those situations we studied. It's to apply it in the future. We have to apply our conclusion in the future. So let me give a really concrete example. We've been really lucky to collaborate with an amazing economist, Rafe Meager. Rafe studies microcredit, these small loans to individuals in impoverished areas. And the hope, of course, is that microcredit is going to help raise people out of poverty. And so what happens is in step one, economists run randomized controlled trials at particular places, at particular times. They gather data on a set of people. They run a data analysis on those people, and they conclude, is microcredit helping people or not? And the whole point is not to say something about those people at that time in those villages in that country, but it's to say, well, if microcredit was really helping people, if we evaluated and thought this intervention was really important and really useful, to apply it on future people, and that's step two. And so in some sense, what we're thinking about with evaluation is, can we trust our conclusions from step one to so-called generalize to step two? So we're really asking questions about this generalization step. And I think we've already heard, actually, I think arguably from the past few talks about cases where we already have some skepticism that our existing evaluation tools are guaranteeing generalization. So we've heard about things like the reproducibility crisis. We've heard about possibilities of overfitting. So I think we already have some feeling that maybe there's room for improvement in our evaluation tools. And so I think there are immediate questions about, well, is there some way that we could deal with that? Ideally, maybe, is there some way that's somewhat automatable that we could deal with that in the spirit, I think, of our conference today? And so let me give you one idea, at least from our research. We ask, well, we might worry that generalization going from step 1 to step 2 might not hold if it turns out I could drop an extremely tiny subset of my data and totally change my substantive conclusions. So let me give you 2 very real-life examples. First, there's a very famous randomized controlled trial of microcredit with over 16,500 data points. That's a ton of work and effort that has to go into collecting that. We find in our work that we can drop 1 data point to flip the sign of the effect. That's the difference between microcredit helping people and microcredit hurting people. And we could actually drop 15 data points. So still less than 0.1% of the whole data to change to a statistically significant effect of the opposite sign. Now, the things I'm talking about today are not economics specific. Let me give another example. So there are these arenas where people look at sort of, comparing large language models against each other. In particular, people are presented with matchups. So there's like LLM1 and LLM2, and the user decides which one has the better answer. And overall, these matchups, people ask, well, what's the best performing LLM? And so if we look at Chatbot Arena, a particularly popular arena with over 57,000 matchups, which was the data that was available at the time we analyzed it, we find we can just drop 2 of these matchups to change the top ranked LLM. Okay, so what does this mean for generalization? Well, I think, even without knowing all the details of these studies, I think we all have a lot of intuition here. If I'm in the first situation, if I were about to, say, invest in microcredit and it turned out that I could drop 1 data point to change conclusion, I'm not poisoning the data, I'm just dropping a data point. Then I might think, I'm actually not so sure this is going to generalize. I want to look at my data more. I want to understand it better. If I'm in the second situation and I want to invest tons of money in the top-ranked LLM because I'm absolutely sure that it's going to be the best performer going forward, way better than the second-ranked LLM, maybe I think, if that all depends on 2 data points, maybe I'm not so sure that it's totally different from that second-ranked LLM. Okay, so at this point, we've said, hey, maybe existing evaluation methods aren't totally guaranteeing generalization. We need to think a little bit about that. Maybe one useful check could be, could I drop a small fraction of data and totally change my substantive conclusions? So let me start with the second point. And notice a first question is that a check that I can run generally? And so that's actually where our research has come in. We noticed that we thought this might be a good check, and it just turns out it's actually impossibly computationally costly to run this check. And so we have some research on how to run this check quickly and reliably in practice, and I'll talk about that in the rest of this talk. And then I'm also going to talk about some other pitfalls and solutions for evaluation, essentially what could go wrong with evaluation in the form of a few vignettes like this. Okay, so in the remainder of the talk, I'm first going to say a little bit more about why. Let's try to really understand intuitively why existing evaluations might not be guaranteeing generalization. I'll talk about this check, this proposed flag that we have. Can I drop a super tiny fraction of my data to change my substantive conclusions? I'll get into a little bit of detail about why checking directly is too expensive, so we had to do something methodologically. We provide an approximation, but crucially with a guarantee on quality. We're going to see a lot of real data analyses and see that some are robust and some are not. And we're going to spend some time understanding that this just isn't the same thing as other types of evaluation you're surely familiar with already, things like statistical significance and other types of robustness. We're then going to talk about how, in some sense in this first part, we'll reveal some assumptions that are important for generalization in existing methodologies for evaluation. We'll talk about some other assumptions as well, and also some potential solutions there. And then finally, in the spirit of our meeting, I'll talk about some implications for automating science. Okay, so let's dig into, why aren't we already solving everything with existing evaluation methods? Okay, so first, let me just give, this is totally not exhaustive, but I think it's illustrative as an example of why, one, existing evaluation methods might not already be solving everything, and two, why we might want to drop a tiny subset of data to see that something might have gone wrong. Okay, so as I said earlier, economists run randomized controlled trials. Medical practitioners do too. Typically, they'll give some randomly chosen set of people an intervention, and then a second randomly chosen set of people not the intervention. So let's think of microcredit, for instance. So these people receive microcredit, these people don't. And then we have to choose what to measure as an outcome. That's pretty tough, but maybe we're interested in something like business profit. The small businesses, did they make profit? Okay, so we can measure the business profit for all of these people and all of these people. And what actually happens in practice is the economists will take the empirical average of the business profit between these two groups. And they'll say, hey, if the empirical average over here is substantively higher than the empirical average over here, then microcredit was helping people. We can sort of immediately see something that might go wrong here. So let's say that we're in a situation where microcredit actually only helps an extremely small fraction of people, or a situation where like a couple of CEOs just happen to wander into my experiment here. Well, now my empirical average, just because it's so sensitive to individual data points, could be very high. But if I removed that tiny fraction of data, I could get a totally different result. And if the whole point of microcredit was that it was supposed to help a substantive collection of people, a substantive amount, then if I can just remove a couple of data points or a small fraction of data from my experiment and change my conclusions, that's suggestive that that's not happening. Okay, so you're probably thinking, I think, very reasonably, well, gosh, we have so many evaluation tools that are literally explicitly designed to deal with generalization. Why aren't they solving this problem? So let's think about what those tools are. Those are tools like, on the statistics side, p-values and statistical significance. On the computer science side, things like algorithmic stability. Tons of people have thought about generalization. Why could it be that even with these tools, we're not guaranteeing generalization? Well, it's because these tools make assumptions that are not precisely true in practice. Does that matter? Well, the tools won't tell us, so we need to check. So let's talk about what those assumptions are. First assumption, the tools assume that the data I have collected and that I'm doing my analysis on is all IID with the data where I'm going to apply the analysis in the future. That's definitely not true for that microcredit example. So the economists run their randomized controlled trial on these people in these villages in this country at this time. For sure, when time has passed, the distribution of those people has changed in some way. And also, presumably, we don't want to apply microcredit in these villages again. We want to apply it in some other location, possibly even another country. And so the people where the policy is ultimately applied are reasonably fundamentally from a different distribution from the people where microcredit was originally analyzed. It's probably not super different. Does it matter that we've made this assumption? Well, we don't know from the tools, and so we need a way to check. Very commonly, existing evaluation tools assume some model is correct. So for instance, let's consider the microcredit analysis that I described to you. Pretty commonly in economics and in medical sciences and other areas, we're effectively using some extremely simple form of linear regression to do the evaluation. There's no way that linear regression is fully capturing everything that is going on in the unique and interesting ways that people are interacting with each other. But it's also worth remembering the famous aphorism by George Box, all models are wrong, but some are useful. We could have an entire AI foundation model. We could have the most complex model that you can imagine, and it's still not capturing all the relationships among people. We could have this for weather, very popular area for AI foundation models now, and there's still no way we're capturing absolutely every relationship among all of the different molecules that are out there in the world. Does it matter that our model is very slightly misspecified in these cases? Well, again, our existing tools might not tell us that. We'd like to have some kind of flag. I think this one's pretty subtle. Existing tools assume the output we are measuring is the output we want. We saw in the microcredit example that this was definitely not true. So remember, in the microcredit example, we measure, and this is definitely what's happening in real life, the empirical average of the business profit in the two groups. We don't care about that. What we care about is that microcredit is helping a substantive collection of people, a substantive amount. The empirical average is a convenient proxy because it's widely used in economics and medical sciences and other areas for evaluation. Does it matter that we're reporting a convenient proxy? Well, again, the tool's not going to tell us that. We might need some kind of flag. And I want to highlight, in some sense, this is because of automation. I mean, this is a success story that AI and machine learning and statistical methods have become so popular that they're just so extremely widely used that they're used in a standard form, which might not be a perfect fit for exactly what we want to do. That's great. It's great that we have these tools. Does it matter that there's this perhaps slight discrepancy? Well, we'd like a check. Okay, finally, data is often missing in some form. So certainly it is the case that in something like a microcredit analysis, there will be some people who leave the study. It could be in a biased fashion. It could be that they leave more from the people who received microcredit or from the people who didn't. Same thing with medical studies. Extremely common to have these issues, even biological studies. So existing tools, to the extent that they assume data can be missing, assume data is missing at random. But of course, in real life, small fractions of data are often missing not at random. Does that matter? The existing tool isn't going to tell us. It would be nice to have some kind of flag. Okay, so hopefully in all of these cases, we have a sense that existing tools for evaluation are not already solving our problems for us. And in particular, we'd be concerned if we could drop a super tiny fraction of our data and change our substantive conclusions, because it is in some sense an indicator that perhaps our assumptions were incorrect in a meaningful way. Okay, I want to make a couple of high-level comments. So one is, I'm going to talk a lot about economics, in part because we got to collaborate with a wonderful economist, and also really because economics is such a reproducible field. And so I hope nobody sees this as some kind of like gotcha for a field. I think if anything, everything that I look at in this analysis and everything I show you today is awesomely reproducible. And so we already had this nice discussion earlier about reproducibility in the previous talk. This is like the first bar. And so these are all fantastic papers from that perspective. So like, just don't read this as a gotcha. Okay, let me talk about what the bar is here. Essentially, we've already said no current check is a cure-all, and I'll tell you right now, I'm not planning to say that ours is either. In fact, I'm going to show you some other different problems later on in the talk. What I'm hoping to convince you of is, one, that our check is often very useful, and two, that we really need to think about evaluation broadly and non-trivially when we're evaluating science. And so I'll come back to that at the end of the talk as well. Okay, let me just give you an example of a case where you would not care about our check. So let's suppose that I'm interested in an analysis of a very rare disease. So maybe I have 100,000 people over here in a city, and 9 of them have the rare disease, and I have 100,000 people over here in a different city, and 6 of them have the rare disease. I would not care if I could drop a super tiny fraction of data and change my conclusions, because I could just drop everybody with the rare disease, and I wouldn't have any disease to study. Conversely, if I'm comparing these two cities, I should probably be upfront that in some sense, I kind of really only have 9 and 6 data points, not 200,000 data points. Okay, so at this point, hopefully we have a sense that existing evaluation methods might be super cool and yet have gaps, not always guarantee generalization, that this tool could be useful for dropping a super tiny fraction of data. And so now I want to get a little bit into practicality. Can we actually even ask, can I drop a super tiny fraction of data and change conclusions? Okay, so in fact, we need to provide an approximation. So at the very beginning of the talk, I mentioned this randomized controlled trial of microcredit. In fact, it's Angelucci et al. 2015. Super cool, fantastically reproducible paper with great data sharing. They have a randomized controlled trial of microcredit in Mexico. As I said earlier, it has over 16,000 households in it. Okay, so let's suppose we were concerned if I could drop 0.1% of my data, an extremely tiny fraction of data, and totally change my substantive conclusions. Well, that means I have to ask, could I drop this 16 data points and change my conclusions, or this 16 data points and change my conclusions, et cetera, et cetera. There are about 10 to the 53 subsets of size 16, or 0.1% in this data set. I'm not even looking at things less than 0.1% here. If you've ever run a data analysis, you know it's optimistic to say that my data analysis could take 1 second to run, but even in that crazy optimistic scenario, this check would take over 10 to the 46 years to run. Here's a case where you could have all the compute of OpenAI and Meta and Amazon and every major tech company that's out there, and you're not going to solve this basic economics problem. And so we need some kind of approximation. And so we provide an approximation. It turns out you can run it for minimizers of smooth empirical loss plus an optional penalty. You can actually run it for cases where you minimize a couple of different things. I know somebody earlier in the day mentioned instrumental variables regression, so that would be a case we can cover too. We provide theory to support its accuracy, but let me just take a step back for the moment. Like, you totally shouldn't trust anything I'm saying right now. I mean, I told you we have an approximation, so you know it's not exact, but I haven't told you what that approximation is. I told you we have theory, but like we just spent a moment ago saying that every piece of theory makes a ton of assumptions, and like, are those assumptions even correct? And so I think much more convincing is that we tell you the data points to drop. We tell you the problematic data points. And so at the cost of only one extra data analysis, you can actually just drop those data points, rerun the analysis without them, and then check, did the promised change happen? And so in everything that I'm going to show you today, we did that check. And in fact, that change did happen. So you don't have to trust the approximation or what we did for that. Maybe if we had a longer talk today, we could talk more about that approximation. But any non-robustness is conclusive. It's only possible that we're missing some non-robustness. We also provide in our paper theory and experiments to show that this type of non-robustness reflects a low signal-to-noise ratio in the data analysis. What I want to do with our time today to sort of illustrate that this is a distinctive type of evaluation from other types of evaluation is just show you a bunch of real data analyses and show the difference, rather than get into the math of this signal-to-noise ratio. Okay, so let's go through that. Let's go through a bunch of real data analyses. And in particular, we're sort of asking what makes an analysis non-robust to dropping a super tiny fraction of data. Again, these are all awesome, reproducible, super cool studies. Okay, a first thing you might be thinking of is, gosh, probably it would be non-robust if it was just like statistically non-significant to begin with, right? Like, isn't this just the same thing as statistical non-significance? In fact, it's not. So very famously, there was a lottery in Oregon in the United States where the winners could sign up for healthcare. When I give this talk in Europe, they recognize this as weirdly dystopian, but it's a thing that happened in the USA. So Finkelstein et al. In 2012 recognized this as a natural experiment. You can ask, what's the benefit of healthcare? They had over 21,000 data points. These are survey responders, so already we have potential issues of survey non-response bias here. So again, reasons we might be concerned about dropping a super tiny fraction of data. This study, Finkelstein et al., looked at a lot of things. They looked at the effect of a lottery win. They looked at the effect of actually signing up for healthcare. They looked at so many different notions of health. I think this is just a really fundamentally challenging thing in science and social science. What are you even measuring? What is health? What does it mean to have good health? So I'm not going to show all of those things here, although you can see them in their paper and in our paper, because we reproduce them all. But one of the measures they have of health is the number of days of self-reported good health in the past 30 days. And so we can ask, how do we feel about that? But that's certainly what they reported. And they reported p less than 0.01, a statistically significant positive effect for the lottery win on that notion of health. And we find that we can drop just 10 data points to change that statistical significance. And I want to emphasize, this is not 5% of the data, it's not 0.5% of the data, it's 0.05% of the data, an extremely tiny fraction of the data. So again, the point is here, it's not like we could have just detected this already with non-significance. This started off as a statistically significant result, but we were able to change it. Okay, another thing that I think you might very naturally think is, man, I've heard being Bayesian really handles uncertainty well, and that's a great way to make sure that you're all set on uncertainty. Or maybe you're thinking, hey, some of these economists, they're using like these simple linear models. If we just used a much more tailored model, something that was more specific to this particular application, maybe we would do better. Or a more complex model for that matter. And so actually our co-author, again, Rafe Meager, this economics expert, did what is widely regarded as sort of like the right thing to do if you have a lot of different data sets, or at least a well-regarded thing to do, let's say, which is to have a Bayesian sharing of power, a hierarchical model across the different data sets. So there's these 7 randomized controlled trials of microcredit, and so Rafe did this Bayesian analysis of them. It wasn't just sort of the default analysis. Rafe actually made a number of thoughtful modeling choices that were specific and used the fact that we had here an expert in both Bayesian analysis and in economics, and microcredit in particular, and we still find it was super sensitive. So we can drop less than 0.03% of the data to change a Bayesian notion of statistical significance for the global effect of microcredit. And we find that we can drop 0.1% of the data to change the effect sign. Again, that's the difference between microcredit helping people and microcredit hurting people. So it's not a panacea to be Bayesian or to have a much more complex model that's much less likely to be misspecified. I mean, they're all misspecified. Okay. What about, maybe this is just flagging misspecification. Maybe that's the problem. And so there's 2 perspectives on this. One, we can make simulated data where everything's perfectly specified, and we can find that that's not decisive. You can either be robust or non-robust, depending on the signal-to-noise ratio. 2, let's look at real data. So in some sense, I've only showed you examples in real data so far that were non-robust because that's kind of interesting. So I was biased in presenting things to you. Let me show you a bunch of cases that are now robust. First, there's this cool paper by Angelucci and DiGiorgi 2009. It looks at the effect of cash transfers on consumption. So another thing we could measure instead of business profit is something like food consumption or caloric consumption. They had over 10,000 data points, and we find we have to drop a lot of data to change the conclusions. Let me be clear here. If I had a data analysis where I changed the data a ton and it didn't change the results, I would think this was a bad data analysis. And so it should be that if I drop a lot of data, I change conclusions. I mean, that seems very reasonable. And so in fact, we find that's the case here. We try changing the sign, we try changing the significance, we try changing this to a significant result of the opposite sign. We couldn't do those things. So that was robust. Okay, there's a different LLM arena than chatbot arena. So this is empty bench arena for LLM rankings. And we found that this one was quite robust. We had to drop quite a lot of data in order to change the top one LLM. In this case, some possible things that are going on here that are worth noting is empty bench has very carefully designed prompts, specifically designed to show differences between LLMs, whereas Chatbot Arena we saw earlier was user submitted. Chatbot Arena uses expert annotators versus empty bench uses expert annotators versus Chatbot Arena uses crowdsourced preferences. If you pay attention to tennis, you will probably not be surprised to know that Djokovic is robustly a top 1 tennis player from recent data. Okay, another thing you might be thinking of is, okay, well, great, you have another outlier detection method. We have a million outlier detection methods. In fact, this is not an outlier detection method in the following sense. We can have analyses that have absolutely no gross outliers and are still sensitive or not sensitive under our metric, again, reflecting the signal-to-noise ratio in the data. Without going into too much mathematical detail, maybe I'll just illustrate on a real-life data analysis. So Angelucci and DiGiorgi, the thing I talked about before, looked at 2 things in their paper. They also looked at a spillover effect on the non-poor households in the same village. So the poor households in the village receive microcredit, and then the question is, do the non-poor households benefit? So the original analysis does, in some sense, a form of outlier removal. They remove the largest responses, and we find we can still, even after that, drop 3 data points out of over 4,000 and change the statistical significance. Okay, so at this point, we saw some ways that existing evaluation methods, in some sense, can have their assumptions violated, and that can actually matter in practice. And now we have this sort of flag, maybe that tells us sometimes when it does matter. And now I want to take a step back and say some other ways. This was not an exhaustive list of ways of existing evaluation methods violating their assumptions. I want to say some other ways this could happen too. And to do that, I'm going to focus on the spatial setting. I heard a little bit about this before. Let's look at spatial prediction, a case where I want to predict a response at new locations. Again, this is very hot right now with things like AI foundation models that are focused on weather and to a certain extent on air pollution. Something we're certainly interested in is air pollution prediction. So let's suppose that we're in a situation where we're collaborating with some scientists. They want to know the air pollution at some nature reserves, maybe like some marshlands in Massachusetts, because they want to study the effect of air pollution in these reserves. Well, they're interested in using some kind of prediction because maybe they haven't measured the air pollution value there directly. Where could that AI prediction come from? Where could this prediction come from? It could be from AI, it could be from machine learning, it could also be from a physical model. We've actually heard about all these things today. And essentially the question we want to ask, or the questions are, 1, is this prediction good? How much can we trust it? And 2, which one's better? You know, if I've got a cool new AI foundation model, I presumably want to compare it to an existing physical model, like one provided by a governmental agency, and say, is my prediction better? Is it worse? Is it the same? So these are the questions we want to answer. Okay, so how are we going to do that? Well, here's one pretty ubiquitous method. I mean, I think so ubiquitous that people don't even take the time to describe it. Sometimes they just do it. And that is, we have a bunch of available data. We reserve some of it for training, and then we use the rest of it for validation. So maybe in this particular case, here's our validation data. And we take an empirical average of some loss on that data, and that is meant to be an estimate of performance at the places I want to predict in the future, in particular in this case, at these nature reserves. Is this a good estimate? I want to emphasize this notion of estimating performance, so we can ask, is it a good estimate? Well, it's theoretically justified under assumptions again, and we should ask what those assumptions are. Here are those assumptions. The assumption is that the validation data and where I want to predict in the future are independently and identically distributed, and there's enough validation data. So what could go wrong? Well, first, obviously, I could just not have enough validation data, and that actually does matter. But let's talk about some slightly more interesting things. First, the validation data and the data of interest can be very different in character. In this case, the EPA air sensors, where I likely have data, are sited at population centers. If I'm interested in predicting at nature reserves, those are rural areas, and they're just fundamentally different in character from the population centers. I might go a little bit over if that's okay. Cool. I'm getting close. Okay. 2, even if I just look at the validation data, it on itself is not IID. EPA air sensors are sited with other EPA air sensors in mind, and so they're not independent. 3, the locations of interest are fixed. They're not random, so they're not IID. If I care about a particular nature reserve, I care about that nature reserve. There's not a distribution there. If I care about the city where I work as a governmental worker, I care about that city. That's just my city. Does it matter that we're violating this IID assumption? Well, again, this is the question we've been asking this whole talk. Sometimes it might be fine, sometimes it might not. And let me illustrate some cases where it's not. Okay, so we show in our work via theory and experiments that this standard evaluation method I just described to you can substantially misestimate performance. We look at experiments on air temperature and wind speed, just in the purposes of time, which I'm already over on. Let me show you an example with London flat prices, that is apartment prices. So here, the task is, we want to use validation data to predict how well we're going to do on performing in future predictions for London flat prices. And in this particular case, we arrange things so that we have ground truth for that performance. In general, you don't. The whole point is you want to predict in the future. Okay, so we'll look at the holdout method. We're going to run a bunch of experiments on London flat prices. On the vertical axis, we have the error. Remember, we're estimating performance in the future, so this is our error in estimating that performance. And that error, in this particular case, is in hundreds of thousands of British pounds. And we find that over all these different runs, the holdout is substantially different from the ground truth. We want to be on top of that zero line, and in fact, we're hundreds of thousands of British pounds off, or around 100,000. Okay, it's not just that this is an impossible task. We propose an alternative evaluation method that's tailored to spatial tasks. And in this particular case, it does in fact cover 0. We also show in our paper that holdout can misrank predictions. So it can be, let's say, I'm in the situation where I'm trying to compare my foundation model to my physical model. It can be that the foundation model is strictly worse than the physical model, but the holdout tells us that it's better. Okay, and the holdout that I described is not the only way that people compare things spatially. We look at other common methods that people compare things, but they also have similar problems in spirit. Okay, I'll mention one last thing on this topic. Standard uncertainty intervals make the same IID assumptions, and so they can have the same problems. Something that you want from uncertainty intervals is that if I ran them 100 times in 100 different worlds, if they say they have 95% coverage, that 95% of the time they would cover the ground truth. And we find that we can use standard intervals and get 0% coverage in experiments, even though they're promising 95% coverage, but our proposal achieves the promised coverage. This is work that is about to appear in NeurIPS this year. Okay, I'll just say briefly about automating science and then I'll wrap up. I think when we think about where evaluation falls into automating science, and anything for that matter, but I'm focusing on evaluation in this talk, we also want to think about what does it mean to automate science. And for that reason, just as we have this whole talk, I think we want to distinguish convenient proxies from our real goal. Our real goal is that via scientific advances to meaningfully advance human knowledge and help better people's lives. And I think importantly, we should also say we're not misleading people or hurting people, because you could do like a mix of both. We don't want to do the second thing. There are plenty of proxies we can come up with. And I'm not saying these are bad proxies. It's just worth, just like an evaluation, noting that they are proxies. We can do things like ask, can we automate writing papers that can pass peer review? And I think, again, coming back to our theme of evaluation, if we just stick to standard evaluation methods, we can totally pass the proxy. If anything, it might be easier. Because in peer review, sometimes it's easier to do things people are already familiar with, even if they might be wrong. But for our real goal, I hope you've already felt from the things we've talked about today that actually we need to do more. Okay, so hopefully you're convinced that good evaluation matters and also that it's not trivial. And I want to summarize why is it not trivial. Because evaluation methods, even though the way that we talk about them, and I'm as guilty of this as anybody, don't measure performance directly, or at least they rarely do. They estimate performance. And I think we recognize in general that when machine learning and AI are doing estimation, that can be good or bad. And I think we need to recognize that here as well, that it can be good or bad, and we have to sort of really pay attention to that. So standard evaluation methods aren't a panacea. They can be good, and yet still we might need more. Appropriate checks can vary by application. I think this, in some sense, harkens back to some talks today we've heard, like Gary Marcus's talk. We should be running a suite of checks. There's not just a single one that covers everything. But I think on a hopeful level, there's a lot of room here for improvement. By focusing on this, I think we can do a lot to accelerate science. Okay, I'll say one more thing. So I'm just going to point you to, if you wanted to follow up on any references that I talked about today, I put them all here, or at least many of them here. I want to focus on one more thing, and then I'm really done. So after we put our first paper up, somebody who's not us, this guy Michael, wrote this cool paper about how p-hacking is not robust to dropping a small fraction of data. So let me be clear about the implication here. If I have a p-hacked analysis, I can expect it to be not robust in the way I described. It is not the case that if you have this non-robustness, that means you have a p-hacked analysis. So the implication goes one way. I think this is important when we think about automating science because we're in this situation where we have more and more hypotheses. We're testing a huge number of hypotheses. We're testing a ton of them. And so it's very easy to get into things like p-hacking. And so I think for that reason, it's nice to have flags, but also maybe whole new paradigms that think from that perspective about when we're thinking about hypotheses at scale instead of a single one. And I think that's actually work that a lot of people are doing. That's very cool right now. Okay, thank you so much.
Hi, thanks for this talk. It was very interesting. Can you just describe a little bit how this method's different from just bootstrapping or standard errors? Because I would imagine this would cover it, and then if you bootstrap and then some of these large samples are out of these bootstrap samples, you wouldn't get significance.
Yeah, so bootstrap and standard errors are basically frequentist motions of uncertainty. So they're saying, hey, I have some data generating process, and I'm going to use randomness to understand some kind of uncertainty interval over that. And so we're very specifically not assuming any kind of data generating process. And I think that's really key because imagine, again, the situation I described where I have my microcredit randomized control trial, and there's two people who either benefit from microcredit or were just rich and walked into my trial. In that case, if I do something like bootstrap or standard errors, I sort of am saying something like, well, over some data generating process, how would I get these people? And I might, in particular for the bootstrap, just randomly not flag that. Whereas we want to say, actually, we want something sort of adversarial, but without an adversary. We want a worst case analysis. We want to say, hey, these two people were just totally different than everybody else. We want to remove them specifically.
I'm sorry, actually, that was my question, but also related to that would be the quantile regression. I'm not sure if I followed your answer. So if I do bootstrapping, if in the case of 16,000 observation, the case you mentioned that there's one observation, the probability that you would get that one observation would be sufficiently enough for you to find to basically decide that the standard error is wide is going to be very small, right? But in that particular case, so my question, I guess I'm repeating Omin's question, would you not conclude in that particular experiment that the result is not significant if you compute your standard errors using bootstrapping, which is a fairly common approach?
Yeah, my example is more meant to get at in the bootstrap or in a standard error, I'm assuming a data generating process. And here we're very specifically walking away from that. Like if anything, I would say that's the whole point. Because once you make this assumption, now you have to say, you know, okay, this is the population, it has these behaviors and so on. We want to say we're specifically not sure if the population could change. So an example that would have no randomness, for instance, let's suppose I'm a farmer and I farm a ton, I have a huge crop. It's really fantastic. And I want to tell my friends, hey, come out here to where I'm farming. It's going to make you a lot of money. Well, it turns out that I live in a desert, and actually a tiny, tiny bit of my land is on an oasis, and that's where all my crop is. There's nothing random about this setup. There's nothing to bootstrap. But there's sort of a sense of which this result, this idea that you're going to make a lot of money on this land by farming, is just because I have this tiny amount of land that is an oasis. And so I don't want to think this is going to generalize that if somebody else comes out to the desert, they're going to make a ton of money farming. And so my point is, this is really about getting away from the distributional assumption, which you're going to have with the bootstrap. And you are going to get different behaviors, but I think it might take a little bit more time than we're having in this like little Q&A to see where those different behaviors are arising. But I'm hoping that's at least a little bit illustrative.
Tamara, fantastic talk. My question is a little bit meta, perhaps a little bit poorly framed, which is that do you think that the field and these ideas are at a level of clarity that we could actually automate this, which is to say that is it possible, for example, we could have a procedure by which, given an experiment, a system can propose the right way to evaluate, not the right way, but a robust way to evaluate it? Do you think that future exists, or do you think that it's far too complicated to do it?
Yeah, so let me say some negative and some positive things. So I think the positive thing is, I don't know, I feel like we're doing it. Like it seems plausible to me that we could at least get close to automating it eventually, or at least automate it at the level that many people would do any of these things. I think that's totally reasonable. Are we there yet in any sort of optimal way? I think no to that one. And so let me just give an illustration. Let's suppose that I find that I could drop a small fraction of data and change conclusions. I think because there are so many ways I could get there that right now I wouldn't feel comfortable saying what's the next step. So for instance, maybe I got there via p-hacking, in which case I need to go back and think about my experimental procedure. Maybe I got there because my cat stepped on my keyboard at the end and messed up some of my data, and then maybe the answer is I just go back and find out what that data was before. Maybe I got there because, so something that we see in the paper is that you can just have a big blob of data, and the nature of a p-value, as people typically use it, is that you're using a standard error. That standard error decreases at a rate square root of n, with n is the number of data points. And so just by having an extremely large amount of data points, you are eventually going to get a statistically significant effect using a standard error. We don't have that problem here. This is a distinctive thing about this method versus that. But you have this issue that sort of, you are just going to get statistical significance doing this, and so you might be, you know, non-robust just because you have this big blob of data and nothing is going on with it. And so in that case, the real issue is there's nothing going on with your data, and so you really want to like step back and not make that claim. And so my point is, there are a lot of different ways I could get to this non-robustness, and I don't feel comfortable saying there's an automated answer once I've done that. And so I don't think this is fully automated yet, but I do think it could be part of a human in the loop kind of pipeline where maybe I'm running so many things that I run this check when I run them, because I think right now something that's absolutely happening in science is people are running sort of default evaluation methods and maybe not running these kinds of checks. And so if I do that and I have this flag, maybe I have fewer things to look at as a human. And so that could be something that accelerates what I'm doing. So I think a number of people have made this distinction between accelerating science and automating science, and I'll do that here too. So I think this could be accelerating without automating.
And I think it's getting particularly pertinent because there are a lot of groups out there creating these automatic scientists. I missed the morning's talks, but a whole bunch of companies and groups creating these things, which sort of include tools for example, statistical testing.
Absolutely.
So it seems like the automated statistician is sort of somewhat hidden away in one of those, and you know, being able to automate this would be great.
Yeah.
Thanks.
So I might take the last question. So when I think about the implication of your work for automating science, I feel like there's sort of two pieces in here that I take. So one is because you're sort of identifying this procedure, this is another area where we might have had sort of false confidence in a result, and we're now having these techniques which allow us to sort of have an assessment of that and be able to say, maybe this isn't as robust as we might think. We maybe shouldn't put too much weight on that. We should do something else. But I feel like the other thing that this is saying is that as we violate these underlying assumptions about models, right, it isn't just that doing like more science would solve that, right? If you, in your case of EPA monitor stations, right? If we said, oh, we're going to have AI, like our worry was that science wasn't robust, so now we're going to have 10 times as many observations, right? Because now we can automate science and it's going to be great. You would still get the same problem because it's actually a model misspecification problem.
Yeah.
And so like this is sort of saying that the extensive margin of just doing a lot more science doesn't necessarily solve these problems, and we may end up all kinds of bottlenecks of like actual restrictions in the world about how these things are measured or something similar.
Yeah, I think this is, in particular, the second one to me is a great point worth emphasizing. I think relates to the discussion we were just having here too, and I just want to point it out again. For the two things I talked about today, the robustness to dropping a small fraction of data and the spatial validation and uncertainty, these are problems that are not solved by simply scaling up the amount of data. So you can still be robust to non-robust to dropping a small fraction of data. And if anything, we phrase things in terms of a fraction. You can still be systematically biased with the holdout with any amount of data, because it's a systematic bias. And so you could convince yourself, I've got so much more data, these things are working well. And if you're using traditional tools, in particular, you could convince yourself that you're doing well in the way I just described. So again, a standard error is going to go to 0 just by getting more data because of the square root of n scaling. Because your model is definitely misspecified, it'll eventually go to a very slightly non-zero value, and so you'll conclude statistical significance. And so this is really saying, hey, we want tools in some sense that address our modern large data world that can still flag systematic bias or non-robustness that can exist even when you have a lot of data. And I'm not saying that this is, exhaustive for that. If anything, I think there's been a lot of really cool tools that are related to statistical hypothesis testing that focus on these kinds of ideas. But I think that's the kind of tool we want in the large data world we live in.
That's a great place for us to stop. Thank you very much, Tamara.